So we are working on our functions, which you have done a lot with functions in the past. Let's erase that. So if we're talking about functions, can you guys remember anything that you learned back in Algebra 1 about functions? What? Nowhere. This is us talking. Okay. Vertical line test. Amir? That is a type of function. Yeah. Yeah. That's actually going to be our unit 4 is exponential functions. Anything else? Yeah, we got our vocabulary words, our domain and range. Remember how we tell if something is a function? Vertical line test is how we tell if it's a function when we have a graph. If we don't have a graph, how can we tell if it's a function? Gibson? The x's don't repeat. If they don't repeat, then we have a function. If they do repeat, we do not have a function. Is any of this sounding a little bit familiar? Our function notation, f of x or g of x or h of x, but it's a letter and then parentheses and another letter, usually x. So what we're doing today is we're taking our knowledge from functions and we're going a little bit further with it now. So yes, you know how to figure out if it's a function or not, but now there are more specific kinds of functions. Our first one is whether it's a one-to-one function. So to figure out if it's a one-to-one function using a set of points or a table, you first have to make sure that your domains do not repeat. Domain doesn't repeat. So if your domain does not repeat, that first of all tells us it is a function, so we can go ahead and keep testing to see if it's a one-to-one. So to make it a one-to-one is your range can also not repeat. So in a one-to-one function, nothing repeats. Your domains do not repeat, your ranges don't repeat. So if we have a graph and we're trying to tell if it's a one-to-one graph, it has to pass your vertical line test. That tells us that it's a function. A one-to-one function also passes a horizontal line test. And that's what tells us it's a one-to-one. And then our other kind of function, we call it an onto function. That means that all of the y values are used. So all of your range values are used. Then it's a function that's onto. And then sometimes it can be both. It can be one-to-one and it can be onto at the same time. Or it won't be either of them. It would be just a function. So we're going to determine if the following is a relation or a function. And if it is a function, we're going to determine if it's a one-to-one, onto, or both. So let's take a look at our first graph here. If we do our vertical line test, if I draw a vertical line anywhere in this graph, how many times does it hit it? Once. So that means this is a function. So now we're going to see if it's one-to-one. So if I draw a horizontal line anywhere, where does it hit it? Hits it twice. So this one fails our horizontal line test. This is not one-to-one. So then we have to see if it's onto. Will it ever use the x values down here? No, it's never going to be anything lower than, what is it, -1, 2, 3. It's never going to be anything lower than -3. It won't be -4, -10. So is it using every y value possible? No, because there's this whole part of the graph it won't go to. So this is not onto. It's not using every possible value. Okay, so let's take a look at the second one. This right here, is what's referred to as a mapping diagram. I don't think you've really done too much with it yet. Your mapping diagram is very similar to your table of values. Your first circle here, that would be your domain or your x values. Your second circle here, that represents your range or your y values. Just like in your table, your domain goes first, your range goes second. So taking a look first, is this a function? Well, what the arrows tells me is this domain value goes to one value of my range. The S goes to 1, P goes to 1, Q goes to 1. So this is a function. My domain is not repeated. It's not going to two separate y values. So then the next question is this one-to-one? So we have to take a look. Is our range value ever used more than once? No, the 3 is used once because it's got one arrow, 5 is used once, 2 is once, 7 is once. So that is a one-to-one function. So then the other question is it onto? Is every single y value available used? No, I have an 8 there that's not used, so this is not onto. All right, let's try our third one. Let's first figure out, is it a function? So if we look at all of our domain, does it repeat? Nope. So this is a function. So next we're going to see if it's one-to-one. So let's look at our range values. Do any of those repeat? Yes, the 2 repeats. So it's not one-to-one. And then to figure out the onto, we have to read this little part here, where all the points are elements of the reals. Remember, that funky little r is how we represent the reals, which is that big, huge number system that has fractions and decimals and negatives and positives and square roots, irrational, rational. So are we using every real number available? No, I've only used a -1, a 2, and a -3. I haven't used them all. So this is not onto. So with our fourth one here, when they give you an equation, easiest thing to do is sketch yourself a little picture. What kind of equation is that? Y equals 2x plus 4. Anybody remember? Begins with an L. Linear. We've got a y-intercept of a +4. So again, since it's just a sketch, I'm going to kind of estimate there. I've got a slope of +2, so I'm going to draw myself a positive sloping line. There will be arrows on the end. That's going to keep going on forever. So then we'll go through our little list of questions. Is this a function? Yes, this would definitely pass our vertical line test. Is it one-to-one? Yes, it would also pass the horizontal line test. Anywhere I draw a horizontal line, it will pass it. It'll only hit it once. Last question, does it have on, is it onto? Because of these arrows, remember that graph's going to keep going on forever, so it will eventually use every single y value. So it does have onto, so this is an example of both. It's one-to-one and it's onto. Our next one's a little tricky because it's more abstract, but person to social security number. So does any person legally ever have more than one social security number? No. So your domain, which is your persons, all go to one social security number. So this is a function. So then for the one-to-one, would any social security numbers ever be repeated? No, not legally. So this is a one-to-one function. So then for onto, again, our range is Social Security numbers. Do we use all of them? No, we still have Social Security numbers that we have to use. So it's not onto. We still have things in the range that we can use. All right, last one. Is it a function? Yes. Is it one-to-one? Yes. Is it onto? Yes. So this one is both. Now the thing with this graph, and I want to explain this to you, because the Regents loves to do this. Since the graph goes all the way to the end, it's implied that it has arrows. So it's going to keep going, and it's going to keep going up, it's going to keep going down. It will use every range value. That's what they like to do. If the graph definitely had a starting and stopping point, like that one that I just drew, that one would not have onto. It's not using every range value. But when they extend it to the ends of the graphs, they're telling you that that graph is continuing on. They don't always put arrows on there. Questions on that so far? Okay. So we're going to do some evaluating of functions here. We're going to do it in 3 different ways. We're going to do it where they gave us the functions you have to plug in. So like here and here. Then we have a picture of a graph, so you find it there, and then a table. So, plugging in, if we look at this one, they want us to take j of 5, subtract j of 3, and then divide it by j of 2. There's actually a pretty easy way in your calculator to do that. We're going to start with j of 5. I got to figure out what that equals. So in my calculator, I'm going to type in a 5. And let's have you guys do this too. And then there's this little button over here above the on button that says STO with an arrow. That means store. So I'm going to take my 5 and I'm going to store it in for the letter X. You push the X. So this is saying you're going to take 5, you're going to store it in for the letter X. And then you hit enter. So now what we do is we type in our function. So alpha y equals gets you your little fraction thing here. Nope. We're going to be in the blank screen. If you hit alpha y equals, if you have an 84, it gives you an actual fraction. If you have the old calculator, you got to use parentheses. So we're using the j function. We're finding j of 5. So our j function was 2x minus 3 over x plus 1. And when we hit enter, I get 7/6. Now again, if you can't do alpha y equals, just use parentheses. Parentheses around your numerator. So again, if you can't do the alpha y equals, you got to do parentheses around your numerator divided by parentheses around your denominator, which if I do math, enter, enter, I still get 7/6. So if you're figuring out j of 3, you need to be doing first 3, store, x, enter. You got to store the 3 in there as your x first. I'm still working on the first problem. I'm figuring out all my values. So what do we get when it's a 3? 3/4. So now we also need j of 2. So let's have you figure out j of 2 in your calculator. Don't ever want to use 0.33333. So now we can go ahead and plug it in. J of 5 was 7/6 minus j of 3, which was 3/4, divided by j of 2, which was 1/3. I didn't get a negative. Uh-oh. Yes, your calculator needs to put it in parentheses. Fractions and parentheses are best friends. You have to put parentheses around them if you can't do alpha y equals or won't do alpha y equals parentheses.
You just got that decimal, and then what did you click?
Math, enter, enter. What? Now, if we go up here to our next example, we're trying to take f of 3a. We can't use the calculator for that because we're trying to plug in a letter. It only works if you're plugging in numbers. So what we want to do is we want to take our f function. Anywhere we see an x, we're going to plug in a 3a instead. So that's going to become 3 times 3a squared instead of 3 times x squared plus a 3a instead of your x. So now we just use our order of operations and we simplify. So we got to do exponents first. 3a squared would be 9a squared. You've got to square the 3 and you square the a. And then plus your 3 at the end.
How does that work?
How does what work?
That problem right there. Like, how did you get 3 times 3a squared?
Because instead of x, I plugged in 3a, like it told me to.
Yeah.
So now we just multiply 3 times 9, gives me 27a squared, and then plus our 3a, and then there's nothing else we can do. We don't have any more like terms to combine. You don't have a number to plug in for a. That's just our answer there. So for the next one, we're going to have p's in our answer since we're plugging in a 2p minus 1. So again, in the f function, everywhere you see an x, you're going to put a 2p minus 1 instead. So 3 times 2p minus 1 squared plus 2p minus 1. So now when I square my 2p minus 1, a lot of people are still messing this up. So if you need to, write it out twice. But that would become 4p squared minus 2p plus a 1. And then I just brought that one down, 2p minus 1. What should we do next? I would distribute your 3. So it's 12p squared. You could also do that first. You'll still get the same answer. So then we just have some like terms to combine here. Bless you. Negative 6p, and a positive 2p. We still have our 12p squared in the front. That's our only p squared. So negative 6p minus 6p plus 2p. Negative 10p. And then a 3 minus a 1 plus 2. And there's our final answer. Those ones are tricky, but the more you practice it, the easier it will become for you, I promise. Yeah, when you have to plug in other letters, that's when kids start getting a little confused. All right, so our next few questions are going off of the graph. So basically what has happened is they took the function, they graphed it for you, they figured out all the answers for you. All you have to do is find the answer that you're looking for. So if we look at this, g of negative 1, that means our x is a what? Negative 1. We're looking for when x is negative 1. That's what that's telling us. So we go to our graph where x is negative 1. Where's the actual curve? It's up here at what number? At 2. So g of negative 1 gets replaced with a 2. Because function g where x is negative 1 is 2. And then we still have this plus 1 here. We got 2 plus 1. So 2 plus 1 gives us a 3. So that's our answer for that one. So next they want us to find the value or values of x when g of x is 0. So we're looking for when the function is 0, which means it would be along your x-axis. That's where our function is 0. So if we look at it, our line or our curve here hits it 1, 2, 3 times. That means there's 3 values of x when the function is 0. What are those values? When x is -2, when x is 0, and when x is 1. That would just be like if you had factored the whole thing out and set it equal to 0 and got your answers. But instead of factoring it, you just look at your graph this time. So then here we have -3 times g of 2 plus g of 1. I like to use parentheses to remind me of how many things I'm looking for. I'm looking for 2 things off my graph here. So I'm looking first where x is -2. What's the value? 0. When x is a positive 1, what's the value? 0. So -3 times 0 plus 0. 0. And then again for the last one, instead of giving you an equation, they've given you the table. So they did all the hard work. They figured out what the numbers are already. You just have to figure that part out there. So we have 2 times f of -3. So again, this is when x is -3. So I go to my x. Where x is -3, my function is a -5. So I'm going to have 2 times -5 plus, what's f of 5? 3. Because again, that's where x is 5, the function is a 3. And then f of 1, -1. Again, you go to where x is 1, it's a -1. So 2 times -5 plus 3 gives us what for our numerator? And then it's over a -1, so what does that reduce to? 7. That would be our final answer.